Hello and welcome to Toddcast 31. This is starting into kinetics, and this Toddcast will cover the general chemistry information you learn that is applicable and you're expected to know for organic chemistry. And then Toddcast 32 will cover the organic chemistry aspect of the kinetics of what you need to know, which is more from energy diagrams. So sit back and enjoy, or stand up and enjoy, or enjoy whichever way you choose to. But kinetics, the study of rate, is fairly important in OChem in that you can predict the speed of a reaction based on size of molecules. And if you exploit the right way, you can create conditions where a faster reaction is chosen over a more favorable or better reaction. And so it's ultimately why we worry about kinetics, is there's something called kinetic control, where you give conditions so that the kinetic or fastest product will be selected, versus thermodynamic or energy driven, where you create energetic or temperature conditions where the more favorable product will be obtained. So we'll get to that. That'll be down the road. For this one, I want to make sure we can figure out what kinetics are. And so we study kinetics by using spectroscopy at different levels. So different types of spectroscopy. One you're familiar with at this point is UV-Vis. Visible range is from 400 to around 750-ish. UV is below 200, but we typically start around 200 to 400 because that's where the majority of our bonds exist energetically. And so I can study certain absorbances, which will have to do with whatever bonds are present in certain molecules or an overall energy transition of electrons from one level to another. And so UV-Vis is an electronic transition based on the the orbital levels. And so we use it to quantify. The more molecules we have, the more light's absorbed. So it's quantitative. The absorbance over here tells me how much I have. So for instance, at the start of a reaction, let's say time t equals 0 before I add in anything else or before I initiate it, when I first mix the two solutions together, the two reactants, catalyst and reactant, whatever I'm doing, I see I'm absorbance here, absorbance here. This does not mean that I have, let's say, 5 times as much of this as this. What it means is this absorbance is unique for whatever's causing it. This is unique for whatever's causing it. I assume it's 2 different compounds, but I don't know for sure. But as a reaction occurs, I will be able to tell, because if they go down proportionally, then it could be a case of 2 peaks for the same molecule. That is known to happen. But let's say this is for one molecule, this is another molecule at the start of a reaction. I toss them in there. I put everything together. I mix them. I start t equals 0, my monitoring of the reaction. And after a certain amount of time, let's say it's 1 minute, 1 second, 1 fortnight, whatever period of time I monitor for, I notice this peak goes down. A peak grew in here. This peak went down. A peak grew in here. So you'll notice this one went down maybe to, I don't know, about 70% of original value. This one went down to maybe 25%, 20% original value. They did not go down proportionally. So that cannot be the signal from the same, like 2 signals from the same compound. It must be 2 different things. So if this one went down, it's probably a reactant. This went down, probably a reactant. This one grew in, probably a product. This one grew in, probably a product. I don't know for sure. I put a question mark because there is also potentially solvent, which shouldn't go down at all and should be invisible if I pick the right solvent. Catalysts. Oh, I didn't think about that one. Could be a catalyst that goes down and is regenerated in the end. Could be an intermediate that's formed, so an intermediate product, or it could be the real product I need. So reactants will continue to go down the entire time. So these, if they go down, products will continue to grow the entire time. So I don't have enough information yet to make these decisions. So I need to run another trial. So let's go to rid of trial 0. Look what happens in trial 2. So in trial 2, the reactant continues to go down. So this, I can safely say, this is a reactant. I can get rid of that question mark. This one continues to grow. So I can safely say, that's a product. This one stayed the same. This one stayed the same. So this was not here in the beginning, but it grew in, but it stayed the same. So it's something called a steady state. Intermediates are formed at the rate they are consumed. So every time an intermediate turns a product, another reactant can form a new intermediate. So we end up with a condition of a steady state. The concentration stays the same. So this is likely an intermediate. And then reactant, it would continue to go down. Might have been a catalyst in there. So that is my best guess. So we have this reactant, check. Intermediate, probably. Catalyst, probably. Product, yeah, I'm feeling pretty confident. So let's get rid of time t equals 1 and introduce time t equals 3, see what happens. Okay, so here comes T3. Oh yeah, the reaction continues to go down as expected. The intermediate is still a steady state. The catalyst, I feel pretty confident the catalyst because it's not being regenerated yet, so the reaction still is going. Catalysts are there in the beginning. They're consumed and then regenerated at the end of a reaction. Well, you're still forming product, you're still losing reactant, so the reaction isn't done yet. So catalyst is going to stay at a low concentration. Intermediate, I think pretty safe in saying steady state intermediate. And catalyst. I'm going to get rid of those question marks because I'm feeling pretty certain. So that's product, that's an intermediate, that's a catalyst. We can safely say that we have those. Okay, so I'm going to do one more trial. Reactant continues to go down. Let's see if that happens. Yep, so the reaction isn't complete yet because the reactant is still going down, but the intermediate is starting to diminish. The catalyst is starting to be regenerated. When this is flat and this goes up, and then I know it's done. Product continues to form. So I haven't completed it, but I'm getting really, really close. So monitoring what happens over time to the reactant, intermediate, catalyst, and product is essential. The rate we represent is the formation of products over time. So how much the products change over the change in time. You can also monitor as the deplenishing of the reactants. Be careful because if it's a 1-to-2 or 2-to-1 ratio, there's a factor of 1/2 or 2 somewhere in here. And you have to keep an eye out for those sorts of things. But basically, rate of formation of products or rate of decline of reactants is your reaction rate. So we'll toss some graphs. If the concentration starts at 0 and goes up, it must be a product. If it starts high and goes down, it must be a reactant. So that first one, reactant. And the second one, product. Not sure why I did red and black, but there you go. And then catalyst, high concentration in the beginning, it drops, stays essentially 0, and then is regenerated at the end. Intermediate climbs up, forms a steady state, and then diminishes at the very tail end. So these graphs, fairly predictable. Should be able to identify them and understand how they work. Truth be told, this is going to be more important when we do biochem and we do very select OChem reactions that have predictable and, I guess, useful kinetic data. Reaction rate and temperature. Okay, this becomes really important because, again, in organic chemistry, you're occasionally going to have 2 or more potential reactions occurring when you mix things together. Controlling which product you get is an art. The best chemists in the world are the ones who can add things at the right rate. They stir it at the right rate. They heat it to the right temperature. They maximize how much you get. And so it's interesting that if you change your yield from 81 to 83%, it seems trivial in the lab. You'll still get an A no matter what. You do it for an industrial company, and you will get a bonus that year, 50,000, 100,000, whatever it may be, because you just made or saved the company a few $1,000,000. Just yield becomes an essential. So these things matter. Okay. So this graph, hopefully you recall from GChem, it's the number of molecules at a given energy, and these represent 2 different temperatures. So as the temperature goes up, the average energy, this point here and this point here, are going to increase. So at lower temperature, you have a lower average energy. At higher temperature, you have higher average energy. So this represents probably a difference in temperature of maybe, let's say, 25 Celsius compared to maybe 80 Celsius, something like that. What matters is there's something called the activation energy, minimum amount of energy molecules must have. So let's say it's somewhere around here-ish. And that would mean only molecules above that line have enough energy to react. So when it's hot, all the molecules in this area right here, drawn in red, can react. So of all the molecules in the hot solution, maybe 15, 20% represent that area compared to the overall area, have enough energy to react. Whereas if we trace the cold one out, going to overlay it, and the cold one, this percent compared to the overall graph, maybe is 5%. So if only 5% have enough energy to react as opposed to 15, and I'm just eyeballing those numbers, that means it's going to be faster at the higher temperature because more molecules can react. So as temperature goes up, the reaction rate goes up. Absolutely imperative that you know this. So reactions go faster at higher temperatures. That's one of those things that we just observe in every chemistry class, bio, G, and O. Okay, so what happens if the activation energy is lowered? So what happened here, it used to be here, now it moved to here. So I should say was here. So how the heck could you go from an older EACT to the new EACT? How the heck could that even happen? How can you have an older and a newer activation energy? Well, simple. Catalyzed, uncatalyzed. Meaning if I add a catalyst in, I lower the activation energy, more molecules. So instead of it being the red used to be around 15%, maybe it's around 25% now have enough energy to react. The blue used to be around 5, now it's maybe up to 10, 15. So more molecules, all these extra molecules now have enough energy to react. So if you add a catalyst, activation energy goes down and the reaction rate goes up. So two ways to make your reaction go faster. Heat it up, add a catalyst. If you have the convenience of adding heat, that's great. Under certain conditions, unstable molecules, you don't have that luxury, so you need a catalyst. Biological conditions, you can't heat the body up beyond what its limits are. You have to have catalysts. That's why we are enzyme driven to such an extent, because we don't have this option in our body. You can't really raise temperature too much, or we just run into denaturing problems of us. Okay, some rate laws. This becomes important, especially when we look at something called substitution, SN1 and SN2. So rate dependence of a reaction can only go, as fast as the rate determining step, the slowest step in the reaction. So the rate depends on the rate determining step. So if you have two things coming together, you have to figure out, is the slowest part the two things coming together? Is it one of the bonds breaking, or is it the molecules aligning? Whatever part of that mechanism is key, because it's an assembly line. One step happens, another step, another step, another step. The slowest step, you can only go as fast as your slowest step. So let's consider a generic reaction where I have A plus B going to C plus D. I've chosen gas. Reality is in OChem, everything's in some solvent. We don't really do a lot of gas. Occasionally we'll have a gas generating reaction, but it's rare. We do get solids dropping out, but usually it's going to be things in solution. We'll go with phases of gas, 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 and solid. The rate, I don't know what the rate is going to depend on, but because there's an A and B, that is my first guess. So A is an unknown coefficient, B is an unknown coefficient. So I'm going to run two trials. I'm going to look at the initial rate. So the emphasis is the rate you're seeing on the far right is what initially is, because as the concentration goes down over time, the rate goes down. So the initial rate when I have 0.1 and 0.1 molar. So 0.1 and 0.1 molar, 2.17. When I increase the B, notice the rate changed. So I'm going to compare rate 2 to rate 1. 4.34 divided by 2.17 is 2. A2 and A1 are both the same number, so they're going to cancel. K is going to cancel. And I'm going to be left with then the ratio of the B. So again, the canceling will be that equals 2. That equals 2 to the B. So let me get rid of my purple. Let this computer screen do it. 2 to 1. 2B over 1 to the B. So 2 over 1 equals 2 to the B over 1 to the B, which basically means B must equal 1. So we say it is first order with respect to B. This number right there is 1. Okay, when I consider it for A doubles, no change, no change. Meaning increasing A showed no change in the reaction. So it has to be to the 0 power. That's the only way that this rate, this divided by this. So you can do it by inspection. I highly recommend that. Doing the long way is good at one time, but by inspection. Doubled B, it doubled the rate, so it depends on B. Doubled A, no change in the rate, doesn't depend on A. So what we will learn, a little bit of foreshadowing, this may be my electrophile. This may be my nucleophile. And so the rate will depend on the nucleophile, but won't depend on electrophile, or that's going to be absurd. It could nucleophile, electrophile. And you'll know why that seems absurd. So in other words, I can identify which is which based on that. So the nucleophile comes in and attacks the electrophile. So two possibilities. Electrophile can fall apart and then get attacked, which you would only see it depend on electrophile. Or a nucleophile can come in and attack electrophile, meaning it depends on both of them. And that is the crux of what we care about. So knowing what I know about this reaction, when I first assigned it electrophile and nucleophile, oh, that can't be right. Electrophile always is going to be involved. Nucleophile may or may not be involved. So A was my nucleophile, B was my electrophile. I can actually identify that from the data. Doesn't make much sense now. When we get an SN1, SN2, it hopefully will. Okay, so let's consider parts of reaction. If the first step is slow, second step is fast. Step 1 will be your rate determining step. So this is how I'm going to hopefully figure out the mechanism. We know from before that it's K times B. And I'm going to say B equals electrophile just because I want to be way ahead of myself. This is a couple podcasts away. Okay, so what probably happens is B, the electrophile splits apart into carbocation and a leaving group. And then this carbocation reacts with the nucleophile to form the product. That is my guess. So breaking the bond, having this group break apart and leave, is the high energy slow step. Once it breaks apart, this nucleophile is going to come in and react very quickly. So overall, let's see what cancels. Product and reactant, so it must have just been intermediate. C is still there, D is still there, A is still there, B is still there. So that's my overall reaction. So just get familiar with this. A is a nucleophile. B is an electrophile. C is your product. This is what's known as your leaving group. So I'm just going to put shorthand for this because I haven't defined it yet. But very typical reaction will be what's known as an SN1 reaction. That's what this describes. This is the importance of being able to look at the rate data and make a prediction about what's going on. This will make more sense as we get into it, but I need the review. You need to be able to recognize the data chart to realize that it only depended on B. And so come up with a slow step that involves just B without the A helps us to logic and reason out what's happening in the reaction. So reactions go as fast or as low a step, known as the rate determining step. You can only go as fast as the B can break apart. Okay, so analyzing the data. When I toss these things out, zero order, constant rate, I don't care. Doesn't show up in OChem. We will see it in biochem, but it's not a big deal in OChem. In this table, let's just do by inspection this time. A doubles, no change in B, the rate doubles. So increase a factor of 2, no change, and the rate goes up by a factor of 2, meaning the rate depends on A to the first. I'm going to just put a 1 there to represent that's to the first. No change in between trials 2 and 3, B doubled, no change in the rate, so it doesn't depend on B, so it only depends on A, so I'm going to reach a conclusion the rate equals constant times A to the first power. It does not depend on B whatsoever, which means A is my electrophile, B is my nucleophile. It helps me identify that in that substitution reaction. Okay. Second order. Same thing, let's do this comparison. So this one again, just like before, doubled, no change, doubled, so it depends on the first power. So again, that's to a first. This time, A stays the same, B doubles, but now the rate actually doubles. So that means it depends on B to the first. So the rate now equals A times B, which means this is called an SN2, 2 for second order, where it depends on both the nucleophile and electrophile. So this one only depends on electro, depends on elect, and nucleophile. And this one, I couldn't identify it from this reaction. I have to do something else. I don't know which is which. This one I know that's electrophile, that's a nucleophile, and it's an SN1. So let me at least put that up there, what I'm saying. So this is an SN1 reaction, this is an SN2 reaction. And we'll, again, go into way more detail when we get into it, but recognizing the data table quickly, seeing the impact of changing reaction concentration on the initial rate matters. Okay, so graphs, and that'll pretty much finish us in terms of what happens from GChem. So your typical graph, zero order kinetics, the rate is constant. So it goes down by a predictable amount. First order, notice it goes down a good amount, a little bit less, a little bit less, a little bit less. So that means your graph is fast at first and flattens out. Remember, this slope at any given point, the tangent, I should say, at any given point is the slope, which is the rate. The rate of decay of this would be the rate of reaction. So steep slope, it's fast in the beginning, and it slows down over time, which means the rate gradually decays to zero. Second order kinetics, this is just sheer craziness. It's the same graph as here, except it drops really fast and decays. So very rarely will something be second order for a component. Usually a second order reaction is first order with respect to two different things. First order for the nucleophile, first order for electrophile. But there are some instances where you get this crazy data initially. Okay, what matters to us, half-lives. Half-life is when you go from 100 to 50, 50 to 25, 25 to 12.5. So half-life is getting cut in half each time. First order half-life is constant. Second order half-life keeps on increasing. So second order, if you have a second order drug or something depends on the component itself to the second order, those things will linger in the body for a long time. So if you're dosing, you end up giving a very massive dose because it decays so quickly, but you don't have to repeat it because it stays in the body. For first order, zero order drug, they diminish in time, but they don't drop very fast at the beginning. So you have smaller doses, but you give more frequent doses. Okay, data analysis. So I want to look at these numbers a little more carefully. The change in time in each case is 1 for every single trial. So 1, 1, 1, and a 1. Concentration goes down by 0.25, 0.25, 0.25, and 0.25. Same concentration dip per time, so constant rate. And again, we won't see this. This is a scenario you see in biochem, sort of kinetics, but we don't see it here. So this, you may have something called a constant turnover rate in biochem. We won't see it. We see first order or second order. So again, the time change is 1, if I'm reading the data correctly each time. And just like the graph predicted, it goes down a lot at first, a little bit less, a little bit less, a little bit less. It's kind of a uniform drop. So it lost 0.48, then it lost half of that, half of that, half of that, and so forth. And keep in mind, this is perfect ideal data. We never get perfect real life data, but theoretically it works well. For second order, you have a massive drop, 0.63 to begin with. Then that amount goes down to 0.12, 0.07, 0.04, which means we lose almost everything in the beginning, and it takes forever to lose the rest of it. So the key thing, constant decay rate, uniform drop rate, crazy drop rate, and decreasing half-life, constant half-life, and increasing half-life. Stuff that you should recognize, constant decay rate, constant half-life, increasing half-life. Okay, this covers the GChem kinetics we need to know. I slipped some OChem in there just because it is kind of cool and it'll be kind of useful for us. But done with another Toddcast. So hopefully this went well, and I will see you at the next podcast. Bye.